test this myth, they'll need to make a stunt dummy with the same electrical properties as a human body. They'll have to come up with a system to make it pee, electrify a track, and finally, test urine's ability to conduct a charge. So the boys need a dummy that can answer nature's call. They'll start with a skeleton.
Okay, this is actually a nice one. Did it come with a body bag? Oh, man! I'll always miss my old skeleton. It's too bad. He got his head blown off with a Mannlicher Carcano rifle.
In the past, they've encased a skeleton in a product called ballistics gel, which is used to test bullets. The guys think it might work well here, too. It has nearly exactly the same electrical resistance as the human body. They just need to mold it into shape.
We use the vacuum form for all sorts of things. We use it all the time here in the shop.
Let's carry this over and cut it out.
We use it for toy prototypes when we're, inventing something.
The same plastic is used in soda bottles. They'll mold the dummies front and back and join the shells together. Normally, they'd use glue to do that. But Adams made an executive decision. He thinks it'll be quicker just to use tape.
He's looking pretty healthy. I've always wanted my own full-size, visible human.
The same speed that Adam has when he goes through and does a job will elicit an occasional mistake because he doesn't think before he does something.
The next step is to fill the legs with gel. Crucial for the experiment, that will give them the same electrical properties as humans. They make this stuff out of boiled-down animal products like cow hooves.
I know, it's really vile. Stop. Stop.
Adam's tape is not holding.
Damn it. It's leaking from everywhere.
We didn't glue that at all, huh?
No, I didn't. Come on. Oh, slanted. If we get lots of ice in here really fast, we'll be okay.
Ballistics gel sets solid when cool, but they only have 4 bags of ice.
I kind of think
There we go. That's fast enough. Is there a spigot on this garbage can?
No.
Total crapola. This is a complete and utter disaster.
It is not. You've got the legs almost full.
It's a total disaster. I mean, the tape not only didn't hold, but the gelatin acts in a completely negative way upon the tape to render it, useless.
He just kind of forged ahead because, he wants to get the job done, and I normally applaud that, but it's clearly a situation where we need more speed, less haste.
At last, a break. More ice means they'll get the legs set for the experiment.
All right, so both of these guys are special effects artists. They're amazing at putting together these little demonstrations and experiments. But this one, there's going to be a crucial mistake that they're not going to realize because these are not physicists or engineers. Quite a few things are off in the way they set this up.
One thing that keeps bothering me about this is that, urine itself is probably not going to conduct all that much. I mean, we don't really know, but I can't imagine that you're going to be able to conduct current like you would with a wire.
Yeah.
And so the dirty work begins.
Oh, it's warm.
What this boils down to is how much current can we actually carry through about a 1/4-inch diameter stream of urine? And is it enough to kill you?
The guys know it's not just the number of volts in a shock that hurts you, but rather the amount of electricity that actually flows through you, called the current. They can work out how much current will zap a third-rail victim if they know 2 other facts. They need to find out the electrical resistance of urine.
So it's about 10,000 ohms, which is just what we expected.
And they know a subway train runs on about 650 volts. Your home sockets are 110.
All right, so we got all the information we need. Okay, so let's check to see the amount of current that's going to go up a urine stream. The voltage difference is going to be 650 volts. And they measured the resistance of urine to be 10,000 ohms. So the question is, how much current will go through the stream in terms of amps? Ohm's law. Current is directly proportional to voltage. It's going to be inversely proportional to resistance, and that's it. All right, so plug the numbers in. So what do we have? We got 650 divided by 10,000. 0.065 amps. And they will refer to this as 65 milliamps. So the question is, that's 65 milliamps of current. Would that be large enough to kill? So the question is, is that deadly? All right, so you would have 65 milliamps of current going up the urine stream, if that's the case. So would that be large enough to kill?
They'll match the subway with a transformer from a fluorescent light.
If you had a rather robust stream of urine and you were able to spray it up on the ceiling, into a fluorescent lamp, you would probably receive the same effect as peeing on the third rail.
A famous electrical formula called Ohm's law says the current equals voltage divided by resistance. So 650 volts passing through urine at 10,000 ohms resistance means there'll be a current of 65 milliamps. Just 30 milliamps is enough to paralyze your breathing. 65 can give you a heart attack.
So would that be large enough to kill? The answer to that question, potentially yes, right? It can give you a heart attack. So that's how usually you kill someone through electricity. You give them a heart attack. It's large enough to potentially can give you a heart attack.
Part of the myth is true. Urine can carry a shock big enough to kill you. In this dry run, they'll try to pass that current through a tube of donated urine, through ballistics gel, and into a relay switch triggered at 65 milliamps.
We'll be cooking with gas.
And I think we should hear
All right, so let's focus on the relay switch.
the thing click if it's going to work if I plug it in right now. There you go.
That's fantastic.
Something actually worked for a change.
So they've got the body built, tested the urine, now for the bionic bladder.
Well, here on Mythbusters, it seems we'll do just about anything for science. We've got 250 milliliters there. It took about 18 and a half seconds, and that's what we're going to try to replicate with our rail rig. Here I go. Start in now. 5 seconds. 10 seconds. 19 seconds is perfect.
That's a relief. But Adam's still got bladder problems.
So the question is pressure, I think.
Yeah.
Personally, I don't let gravity do my trick. There's some pressure involved. So the question is how to add pressure to the system.
What better way to pressurize a fake bladder than with a whoopee cushion?
Yeah, that's holding pressure.
Better still, it fits perfectly. But, of course, that's only half the equipment.
If you make the stream really small and narrow, the surface tension is going to tend to make it go into a spray or a droplet.
Yeah, I've gone as close as I can to the real thing.
You got to fill it up.
Yeah. Are you ready?
Ready?
Commencing. Wee-wee. Looks like a pretty convincing stream to me.
Yeah.
The science is good. We know why things are working and why they're not working, and getting some really good results. I'm having a great time, as dirty as the work is.
There we go.
The Mythbusters are ready to ride the third rail.
That's good.
Where's the wee ball I have to go? I guess I can weld it until we're down there. Oh, man.
65 milliamps. Through a tube of donated urine, through ballistics gel, and into a relay
All right, guys, this relay switch is the one that you need to focus on. What is that?
switch triggered at
Okay, so it's going to get triggered at 65 milliamps.
65 milliamps.
Okay, relay switch is going to become the heart of the dummy. All right, so if you get 65 milliamps getting to the relay, it's going to trigger. If it's less than 65, what happens? Nothing. All right, so they set it up to 65 milliamps.
Be cooking with.
So if you got 65 milliamps of current going up the urine stream, by the time it gets to the relay, do you think it's still going to be 65 milliamps? Yes or no? Guys, if you got 65 milliamps of current going up your urine stream, by the time it gets to your heart, do you think it's still going to be 65 milliamps?
No.
The answer to that question is no, not unless your heart is located right next to your balls, guys. When you're a teenager, it may feel like it. In reality, you got plenty of shit in between. When I say shit, I mean real shit. All right, you got internal organs, you got internal organs, you got muscles, you got bones, you got a lot of stuff in between. Different internal organs will offer different amounts of resistance. You got fat. Oh my God. I mean, by the time the current gets to the heart, it's not going to be 65 milliamps. It's going to be much, much less than that. So does this experiment have any chance of working under the circumstances? Nope. These people completely missed the point of resistance. All right, these people just missed the point of resistance. This experiment is doomed to fail. It doesn't matter how many times they try it. This thing is going to keep failing. And they're not going to notice why it's going to keep failing. Because that relay is set to 65 milliamps. The current is not going to be 65 milliamps. The larger the resistance is, the smaller the current becomes. That means that the charge will slow down. So the question is, and this is the question that these guys end up missing completely, what is resistance? What causes resistance? Where do we get the resistance from? Oh, in the Disney world, the charge will accelerate from left to right, and they're going to keep accelerating forever. In reality, that's not what happens at all. What happens is the charges are going to end up zigzagging around. So why is it that the charges end up zigzagging around? So what's happening? What's happening is something is resisting their motion. So the question is what? All right. Okay, let's go to chapter 19, lecture notes. It's got more stuff in it. I don't want to keep drawing this time and time again. All right, so we'll need to have a discussion about that. All right, so the inside of it. Charges want to accelerate from left to right. All right, let's just get to this point. All right, so you got the chapter 19 lecture material. All right, so you got your positive charge region, you got your negative charge region. And okay, so what's happening is the following. As soon as you turn on the electric field, charges will experience a force in this direction, so they're going to try to accelerate in this direction. Except the problem is they keep running into these red balls. Okay, guys, what do these red balls represent? Okay, so what kind of resistances are these red balls? So the question is, what do these red balls represent? Okay, number one, don't ever repeat this to anyone outside of this class. Don't say that the Kenneth says what kind of resistance is red balls, all right? I'll track you down and I will kill you, all right? So what do these red balls represent? I don't want to come up with a hypothesis of red balls responsible for resistance. All right, so what do these red balls represent, guys?
Molecules?
All right, so the atoms and molecules making up the structure. All right, these could have been blue balls just as easily, right? So these just represent the atoms and molecules making up the structure. So what's happening is the resistance is caused by the atomic and the molecular structure of the environment that you're looking at. So how much the atomic or the molecular structure impedes the motion of these charges is known as resistivity. All right, so resistivity, the letter rho represents resistivity. So how much the atomic structure or the molecular structure impedes the motion of these charges is known as resistivity. So the main cause of resistance is resistivity, which is the atomic structure that you're looking at. All right, the second contributing factor is the length of the wire that you're looking at. The longer the wire is, the larger the resistance is going to be. The longer the wire is, the larger the resistance is going to be. The third contributing factor is the thickness of the wire. All right, so the thickness is denoted in terms of the area. All right, so larger the cross-sectional area, the smaller the resistance is, which is the same as the thicker the wire is, the smaller the resistance is going to be. All right, so these contributing factors, resistance is directly proportional to resistivity. It's directly proportional to the length. It's inversely proportional to the thickness. Can be summarized into a single formula. All right, so resistance is directly proportional to the resistivity, directly proportional to the length, and inversely proportional to the cross-sectional area. All right, so that's the formula that we will get to use. Okay. Also, resistance is going to be directly proportional to temperature. All right, so let's try to explain how it's related to temperature. All right, so we got one more contributing factor, and we will get to use a different formula for it. Resistance is going to be directly proportional to temperature. All right, so let's try to come up with a reason for it. Why would the temperature influence resistance?
So the molecules move?
Okay, why would the molecules move?
Because that's what they do when they're hot.
Okay, Ian, I'm going to give you 5 points for that one. How do these molecules become hot? What caused them to become hot?
Friction?
All right, friction doesn't mean anything in the atomic scale, so I'm going to give you 5 points for that one as well for rendering a guess at that point. All right, so friction means what on the atomic scale? It doesn't mean it. So here's what I'm going to do. I'm going to give you a different analogy. Electrons, imagine that these electrons are indestructible for tempos. I'm going to give you a trap analogy for this one. All right, imagine that this is a highway, and then you just turn on the electric field. So what happens? These four tempos become energized. So they got potential energy. That potential energy is going to turn into kinetic energy in this direction. All right, so which means that they're going to speed up. They will accelerate near the speed of light. That's what happens. Except it's not your day because I placed these trailer trucks at random places on a highway. All right, now what's going to happen is these electrons will run into these trailer trucks. If you got a one single four tempo hitting a trailer truck, if you're a trailer truck driver, it's not going to register, guys. You will hear the bang, a small vibration. You will go, oh, I think I just got hit by a four tempo. That's it. It wouldn't really register. It wouldn't even bother you. But imagine that you're getting hit from every which direction by millions upon millions upon millions upon millions of four tempos. It's almost like being attacked by the Chinese military, guys. Then what happens? Oh, you will feel it. It starts to cause noticeable vibrations. So what happens is these molecules will start to sway back and forth. These trailer trucks will start to sway back and forth. That's motion back and forth.